All of you, please be seated. Very good afternoon to everyone. It's my pleasure to address Professor Srijit PK. Dr. Srijit PK is an associate professor at the Department of Computer Science and Engineering, IIT Hyderabad. He is interested in developing machine learning, deep learning, and Bayesian learning models to solve problems arising in various domains of artificial intelligence, such as vision, natural language processing, and social media. He has published papers in top venues such as NeurIPS, AAAI, UAI, ACL, EMNLP, ECML, WACV, UMAP, ASONAM, etc. He has been a reviewer for premier ML and NLP conferences such as NeurIPS, ICML, AAAI, UAI, EMNLP, etc. and the senior program committee and local organizing chair for ACML. Prior to joining IITH, he worked as a postdoctoral research at the University of Melbourne and at the University of Sheffield. Dr. Srijit did his PhD at the Department of Computer Science and Automation, Indian Institute of Science, Bangalore. He holds a MTech degree in Computer Science from IIT Bombay and a BTech degree in Computer Science from NIT Calicut. He is going to deliver his talk on continual deep learning, a lifelong learning in neural networks. Thank you very much, sir. And you can just take over the session.
Thanks for a very nice introduction. Thank you for an invitation to be here. So I'm talking about continual learning today. So I was talking about continual learning, specifically continual deep learning models, and how it can bring advances to artificial intelligence program. So the first half of the talk, I will give some very basics. So are you all familiar with this name, continual learning? Basics. And then I will give I will talk about one of our methods on continual learning that we have developed. So yeah, so we all know that deep learning has brought a lot of advances in AI on different domains of artificial intelligence, on computer vision, natural language processing, in speech processing, and even in gameplay, we have brought a lot of advances, and we all have heard of computer beating human champions in different games like Go, chess, etc. And these recent advances are mainly due to three major factors because of the availability of the data and then computing resources such as the GPU and some novel architectures and algorithms that people have developed over the last decade, which brought a lot of advances in training deep learning and achieving this kind of human level performance in several tasks in artificial intelligence. But then we can see that the deep learning algorithms are far from achieving the kind of capability that human learning have. So humans can learn from some limited amount of data. For instance, if you look at game playing, a champion like me, Sudol may have played a few thousand games, while the pro playing machine had to be played around like millions of games to achieve that level of competence. So they are still far from the kind of the level of intelligence that humans possess. And most of the times, humans are capable of solving some tasks by utilizing some knowledge that they have from solving some previous tasks. And that brings us to this domain of continual learning, where we can see that human learning is always being continual. So we solve several tasks in our life, and in solving some particular tasks, we may use the knowledge that we have learned from some prior tasks in solving some new tasks or learning some new skill. So if you look at, for instance, you're say learning to drive some bike. Maybe if you have already learned to drive a cycle, then you can utilize that skill and you can learn the driving of bike much faster. And consequently, that also can help you in driving some car and other vehicles. So now humans have this ability to store and that knowledge that they have acquired from some previous task and utilize that knowledge in solving some new tasks so that they can learn this new task much faster and efficiently. Well, yeah, if you look at the standard deep learning models or any machine learning algorithms, they have been traditionally, used to solve one particular task. So when solving one task, they need a completely new set of data, and they have been trained on that task without trying to transfer this knowledge that they have acquired by from solving some old tasks. So now the question is how we can impart this kind of continual learning performance on these machine learning and deep learning models. And that can be quite useful in several different applications. For instance, if you look at autonomous navigation, so there could be an autonomous navigation vehicle which has to be deployed across different environments. For instance, it has to be deployed in city, and then it has to move to another city or some village or some other, kind of a different environment. And it then again could come back to the city where it has already been deployed first. So in all these processes, it may have to acquire some new knowledge, but at the same time, it should not forget what it has learned before. So this could be one application area where continual learning will be very useful. There could be several other application areas also. For instance, if you look at these chatbots, and they may have to adapt themselves to each user and each different domains, but they may encounter so some domains multiple times, and they should be able to perform well on all these domains without forgetting what they have learned before. Sorry? Yes, probably I can come to that. But to answer that, in transfer learning, you are only focusing on its performance on that target domain. You don't care much on the source domain. So there will be a source and a target. While here, you still be caring much about the source domain, the performance on the source domain. So you should not be forgetting what you have learned on the source domain when you transfer to a new domain. That's a major difference. So, yeah. And then if you look at properties, they can be deployed in different environments, and they may have to perform well on some new environment without forgetting what they have learned from old environment. So all these different applications can benefit if these deep learning models have this ability to learn continuously without forgetting what they have learned before. But if you look at the standard deep learning techniques, and when you deploy it in all these environments, so generally when you go to a new environment, then you will be training it on the data from that environment. And when you train it on the data from that environment, it will forget what it has learned before. And this is, in literature, this is known as catastrophic forgetting. And they suffer from this catastrophic forgetting problem, which prevents them from remembering what they have learned from the past data. So our aim is to develop deep learning models in continual learning. The aim is to develop deep learning models which could overcome this catastrophic forgetting problem that is executed by the standard deep learning techniques. So here is one example of catastrophic forgetting. So for instance, if you simply consider just two tasks, and your first task is simple MNIST classification, and the second task is permuted MNIST. And here in this paper, they have studied how the performance of the deep learning model will change when you move from task A to task B. And here in this graph, they show the performance. And you can see that here on x-axis you have test error on all tasks, and on y-axis you have test error on new tasks. And you can see that the test error on new tasks, so this is like your training on old task first, and then you will be moving to new task. And as the training progresses, so initially when you are training on the old task, the performance on old task will be not very high, but as you move on to the new task, the performance decreases on the old task. But new task performance would improve. So this is what is shown here, that now even if two tasks, as you move from one task to the next task, the performance of the old task decreases. And all these deep learning models suffer from this issue called catastrophic forgetting, where they forget how to perform on the old tasks. And they showed it from different types of tasks, say MNIST, permitted MNIST, and then on MNIST and Amazon reviews, and all these different tasks, even with just two tasks, they observed this behavior. So when we move from some two tasks setup to something like 5 tasks setup, this is going to be even worse. And this is one such example where you consider some 5 tasks where you split this MNIST into 5 different tasks. Task 1 is like you have to do this binary classification of 0 and 1, consists of 0 and 1 digits. Task 2 is consists of 2 and 3 digits, and task 3 is 4 and 5 digits. Task 6 is 6 and 7, and task 5 is 8 and 9. So you need to do this binary classification, and you have some 5 tasks. And what happens to a deep learning model as you train on task 1 and train on task 2, on task 3, etc. And this graph here shows that, okay, initially when you train on task 1, so blue shows the performance on task 1, the performance will be good. But the moment you started training on task 2, that happens here, the performance starts degrading, and as you get more tasks, when you get, say, task 3 and above 14, the performance further degrades and it becomes very low as we have more and more tasks.
So, when we move from task 1 to task 2, are we just adding 2 more nodes in the binary classification?
No, you can think of having separate heads. Yeah, there is a separate head. You can think of having a separate head, which just is binary classification for task 2, and then another head will move to task 3, which is a binary classification for task 3.
So when you are referring this accuracy, is it task 1, task 2, the overall accuracy after going to task 2, or it is only
So here, this is the task 1 accuracy. This shows only the accuracy of
this only task 1 accuracy being training on the task 2, task 3, and so on.
You get task 1 data from 0 to 20 epoch, then 20 to 40 epoch, then you will get task 2 data, but you don't have access to task 1 data. You will have access to only task 2 data.
That will be the accuracy of the task 2.
So what happens? So when you train on task 2, what happens to the accuracy of task 1 that is shown in blue, and what happens to the accuracy of task 2 that is shown in orange?
What is the orange one and what is the blue one?
Okay, orange one is the accuracy on task 2.
Task 2
what happens to that as you train on more tasks? So this is the case, right? So what the experiment they have conducted is that, okay, you have task 1 data. So the idea is that, okay, I will come to that proper definition will be in the coming slide, but the thing is that, you will get different tasks in a sequential order, and you will not have access to all the task data at any point of time. You'll have access to only one task set.
One task at a time.
So you get task 1. So basically, like in a human learning, if you see that you solve one task, and then you solve another task, then you solve another task. So they are trying to imitate that setup where you initially have not task 1 data, and you train on task 1. So that is shown here, like for 20 epochs, you train on task 1. Then you train on task 2, like 20 to 40 epochs, you train on task 2 data. So at that point, you will not have access to task 1 data. You will have access to only task 2 data.
Yeah. Here the question is, when you start the task 1 data, we are training. Just basically trying to understand. So when we start with task 1, we are getting nice accuracy. After the orange curve, when you start with task 2, for the 20 epochs, we are getting nice accuracy. What is actually causing when you suddenly go to task 2? Anyway, you are training for 20 epochs. It's not. what is causing actually to fall down the accuracy?
What is causing is, no, this is what is causing.
Oh, yeah, okay.
Task,
It's completely different one, okay.
yeah, you will be updating the parameters based upon the loads that you compute on task 2 and the gradients you get from task 2. So because you update the parameters of your model based upon task 2 data, so it will get adapted to the task 2, and if you forget, or no, it affects the performance on task 2.
So after updating on task 2, if I come back and basically infer on task 1 with the range on task 2 with the weights and all those things, the finalized model, what's going to happen is
Yes, exactly.
is
So that is what is shown in this plot. So when you train on task 2 data and you check the performance on task 1, it will be less.
yes, that is what and now this is understandable. Yes.
In
Yes.
42 system, you train on task 3 data
Yes.
and see the performance on task 1 and task 2. You
Yes.
can see that it degrades.
Yeah, this makes sense. Now this makes perfectly sense. Yes.
Thanks for that.
Yes.
Okay, so that is what is basically happening here. These parameters get adapted to the new task, and because the parameters are getting adapted to the new task, it may fail to perform well on that earlier task, and consequently affect the performance on earlier task.
But humans also fail actually, especially in the exams.
So students, so they may also forget some tasks they have
Yes,
learned.
exactly.
And most of them, the skills they have learned, it may stay with them. Maybe you have learned swimming or something.
Yeah.
cycling. That most of them will stay with them. But
Yes,
maybe some sort of very specific task, yeah, they can forget it.
yeah, studying and exams. Yes.
Sure. So yeah, so this is so from the classification point of view, if you look at these are some say positive classes data, and these are negative class data. So what you do in the classification task is to learn a function which separates the positive classes and negative classes, right? And for this is how the positive classes and negative classes are for some say task 1. And for task 2, this is going to be slightly different. We just going to pictorially show what happens to the decision boundary. The task 2, this is going to be slightly different. The positive classes are like this and negative classes are like this. And an ideal decision boundary will be something like this, which separates out positive from negative. But then if you go with this decision boundary, then it is going to affect its performance on task 1. The task 1, the classes were like this and like this, while the decision boundary that you have learned is not going to perform well on task 1. So what you want to end up learning is some decision boundary like this, which would result in learning or giving a good performance on both these tasks. On this data, which is coming from task 2, as well as this data, which is coming from task 2. So, yeah, so your goal is to learn such a decision boundary, which is capable of performing well on all the tasks that we have seen. Yeah, so if we, just to define what a task is, which machine learning, okay, all these different types of tasks that we solve, classification or regression or distribution like object detection, segmentation, etc. All those can be seen as a task. And we will be possibly getting different tasks. It would be different tasks of same kind or different types. And typically in machine learning, what we do is that we learn a model for each task completely based upon the data from that task. But in the case of continual learning, what we have to achieve is to learn continuously without forgetting what we have learned from previous tasks. So that is what is shown pictorially here. So you can think of this What's shown on the left side as single task learning, where you get data from one particular task, say T1. Here's X and Y, the data follows some distribution D1. And you have a machine learning model, so a deep learning model or any model, which learns from this data. And then at the time of testing, you will get some input from this distribution D1, and you try to predict the output for the input that you get. This is the typical standard machine learning setup that you have. So in continual learning, you can see that you will get data from multiple tasks, but in a sequence. Like you will first get data from task 1. So task 1 and this data as well as input output follows some distribution D1. Then you will get data from task 2, where the input output follows some distribution D2. Then some task n, where input output follows some distribution Dn. But this task comes in a sequence. You don't have access to all the tasks at once. So when you have access to all the tasks at once, that is, in machine learning, that is called by some other name. What's it? Multitasking. So when you have access to the data from all the tasks at the time of training, then it is known as multitask learning, and people have developed setups or methodologies to do multitask learning where you want to share knowledge across different tasks. But here, you will have access to only one task at any point of time, the data from one task at any point of time. While at the same time, you may want to perform well on the data from any of the previous tasks that you have seen. So at the test time, you may get data from task 1, you may get data from task 2, you may get data from task 3. And you may want to perform well on the data from any of these previous tasks that you have seen. So that is what is shown here, and that is the objective in continual learning, and that's how it's different from multitask learning.
When you define the task, like, can you say that if classification and regression can be combining, or are we fixing the setting?
So generally, so far most of the work that has been studied considers homogeneous tasks. So you have multiple classification tasks,
But not the
different types of tasks. Okay, reinforcement learning is a completely different setup where you get some label or some feedback after you make some decisions. You make some sequence of motion, at the end you will get some feedback. Right? So here, each task can be any classification, supervised learning task, so you can be an unsupervised learning task where you have this output for every input that you get. You assume that each of these input is ILD. But of course, each task can be a reinforcement learning task also. Can be any machine learning task. That can be a supervised learning task, can be a unsupervised learning task, or it can be a reinforcement learning task.
Can data be different modalities? Tasks.
So technically, you can have data to be different modalities, but then people have doing research on that, how to deal with the cases where you have different modalities of data coming has to be a different task. So you can have a language data, or you can have vision data. So practically speaking, that can be considered, and your objective is to learn continuously about different modalities of data. But at this point of time, people there's not much work on that because.
That is very interesting for automotive sector. We have different sensors, data is coming differently, also different modalities. That is, I think, it is very good scope.
Sure, we have some work going on in that direction. We have some 100 projects on that direction where we have a continual learning setup where we have data from different modalities and how do we learn that over different sequences. Yes. So currently the research is happening in that direction. Then mostly you take that as a different task. So when the distribution changes, distribution shift happens, you consider that as a separate task. So generally in the machine learning setup, one task, anything one task, it consists of data coming from the same distribution. Yeah, so this is what it is, and under this continual learning framework, we have studied several different setups containing different types of tasks, etc. But most commonly studied framework or paradigm is these three, something called task incremental learning, domain incremental learning, and class incremental learning. So in task incremental learning, so the idea is that okay, you need to solve these as a classification problem. So your task one consists of images from say classes 0 and 1, and you want to solve this as a binary classification problem. And task 2 is images 2 and 3, and you want to solve it as a binary classification problem. And you have multiple binary classification problem, and you're also given information that okay, this data belongs to task 1, this data belongs to task 2, this data belongs to task 3. So that information or task ID is given to you. So along with the data input output, you are also given the task ID, and based upon the task ID and the input output pair that you have, you need to do the classification of the input. So that is generally studied as task incremental learning. And in domain incremental learning, so you don't really care whether you want to predict, say, if you're given some input to, you don't really care whether you want to predict as 2 or 3, but you only care about whether it is belong to positive class and negative class. So in domain incremental learning, basically for a given input, you just predict it as 0 or 1, positive class or negative class. You don't exactly try to predict whether it is like 2 or 3 or 4 or 5. And also you don't really need a task ID to do that, or task ID is not given to you in a domain incremental learning setup. And in class incremental learning setup,
So, domain with the new task, it's coming from new domain.
like the domain or the input distribution will be different. Input data distribution will be different. But you make incremental learning setup. So a practical application would be like you need to do say something like product review. So sentiment classification, both the individuality of say product reviews and the sentiment classification of say movie reviews. So those it can be seen as like domain incremental learning system, where you just want to know positive and negative like binary classification, but your data would be in a slightly different domain.
Restricted to only multi-class. We can have.
No, it can be, yeah, it can be non-multi-class classification, not classical binary.
So, anything that is coming from a different.
Yeah. So more specifically, your output space would be same, but your input space will be from a different distribution.
Isn't that similar to domain adaptation? If the output space is same, but
Yeah, but in domain adaptation, again, you only care about your performance on the target domain.
we don't care for both the domains.
Let me start. So, and also typically it is like pair of things, like there's a source domain and target domain. So now in this setup, you'll be having multiple such tasks, and you care about your performance on all those tasks. So that's how this is going to be different from just a domain adaptation. And class-independent learning is a slightly more complex setup, where in the end you need to finally do a multi-class classification, and you are also not given a task ID. So you get some task 1 where you want to do a classification into 0 and 1. When you get data from task 2, then you want to make classification into 0, 1, 2, 3. So you need to consider that exact class associated with the data of second task also. And at the end of it, you want to do a multi-class classification, classifying into 10 different classes, and without the knowledge of the task associated with that input data. So you don't get the task ID associated with any of these input data, and you want to classify that into these 10 different classes without knowing the task. So that's a slightly more complex setup, and that is typically studied as class incremental learning. So these are the different learning setups which you can see corresponding to the different real world setups that we may go back in different applications. And typically people try to develop algorithms, continual learning algorithms, which could perform well on all these three different setups. So our objective in developing continual learning algorithm is mainly this. So you will see tasks in a sequential manner, and you have very limited amount of memory. So you cannot store the data from all the previous tasks that you have seen so far. So you have a very limited amount of memory and computational resources, and you want to learn from each task, and then you want to move from next task without forgetting what you have learned from previous task. Because you don't have enough memory to store all the data from the previous task and again perform learning over all the data from all the previous tasks. So you want to avoid all these, and you want to learn continually without forgetting. That is the objective. Yeah, of course. Now we want to avoid forgetting on previous tasks, because at the prediction check, we may encounter data from all the tasks, and so we want to perform well on all the tasks. And in this process, as we have already mentioned, like humans often make use of what they have learned before in learning a new task. So this process of using previous knowledge to learn a new task or more effectively learn a new task is known as forward transfer. So we want to transfer knowledge from previous tasks in learning some new tasks. So how we can enable this forward transfer, or how we can accomplish this forward transfer in a continual learning system, that is another objective that we want to achieve. And again, backward transfer. So when we learn a new task, that can possibly improve the performance on all the tasks. And how we can achieve this backward transfer, that's again another objective of continual learning. So in general, you can see the objectives that we want to achieve in continual learning as all these, like avoid forgetting, enable forward transfer, enable backward transfer, and we need to achieve all this with some very fixed amount of memory and computational power. So this is the objective, and people. Okay, so this is like one way to look at it, what we want to achieve. So you can think of having some three tasks: task 1, task 2, task 3, and generally, when you move to a new task, you just fine-tune your model with data from new task, and that will result in forgetting what you have learned. And that's not here. So when you fine-tune your model on new task, the performance on first task decrease, and when you encounter third task, the performance on first and 2 decrease, and you will get a good performance on task 3. So this shows forgetting or lack of stability, in other words. And when you don't fine-tune, you don't change the parameters at all, then the performance will be remaining same on task 1, but it will be poor on task 2 and task 3. Okay, this is known as lack of plasticity. And when your model is both stable and plastic enough, then you can get a very good performance on all these tasks. And in addition, if you enable some forward transfer, the performance could even improve on subsequent tasks by transferring some knowledge from already learned tasks. And in this case, you enable backward transfer, then the performance on prior tasks also can. So these different objectives are pictorially represented here. And this is something that we want to ideally achieve in a continual learning setting. And there are.
Why is it about the path, like task 2 and task 3? What does it mean going about the path?
Because there is a forward and backward transfer that has happened. So if you had learned the task independently, you could achieve only this much performance. But because of that backward transfer, the performance has gone up. Yeah. People have come up with several techniques to achieve these objectives, and not that all the techniques will be able to achieve all the objectives. and few techniques were able to achieve few of them, not the others. So these techniques can be, in general, be classified into three groups. One is replay-based techniques, and second is regularization-based techniques, and third is parameter isolation techniques. So I'll give you a brief overview of what this is. Like in replay-based techniques, one can think of just storing some subset of data points from each of this previous task. And then when you train on a new task, you use those data sets that you have already stored also in training on new tasks so that you can still achieve a good performance on priorities. So this requires some storing of previous data. And so maybe some limited amount of storage, limited amount of data, some exemplars, which can be representative data points of previous tasks you may store. So that is replay-based techniques, and people have come up with ways to avoid that also. For instance, one can use a generative replay, then one can use generators such as variation of encoders or generative adversarial filters, which can be used to generate data from previous tasks. So these generative replay models doesn't require to store the data, but they may have to store this generator, which could generate data of the previous task. And regularization methods, so they use a explicit regularization term, which prevents the previous parameters to be overwritten. So if when after you learn on one task, say task one, if you find some parameters are very important for task one, and these regularization approaches, what they do is that they avoid those parameters to be overwritten when you train on task. So they come up with regularization techniques which will avoid important parameters to be overwritten, and they retain those parameters values to be as it is for subsequent tasks, so they may perform well on previous tasks. And architecture-based methods, we may try to modify the architecture, say for example, add new layers or add neurons when you move to new tasks, or do some masking where you mask some set of neurons for each task, and do some modifications in the architecture to address these, to achieve this. So yeah, so there are all these techniques are there. Maybe this is a good survey where you can find all these different techniques. But now I'm going to do this on our work on continual learning. This is a joint work with Srikar Tripathi. He is joined in the AI department. Got accepted with WSA in 2023. So what we did is we come up with a continual learning based upon hypervectors, where model-based hypervectors as so we talk about that in the coming slides. So any questions? Any other questions, sir? Because you updated or you updated these parameters for task one first, right? And can you never have access to those data? So that's no, may not be always the case that the task one performance will be the lowest. For instance, consider a situation that with task 3 you encounter some task 3, and task 3 is very similar to task. And if task 3 is very similar to task 1, it could happen that the task 1 performance also could improve and could be better than task 2. So, may not be always the case that the task 1 performance always goes down and task 2 performance. That sequence may not always happen. It depends upon the kind of similarity among the task groups.
Since as you mentioned that when you're using an external memory, that should not go in a sublinear time, sublinear space, right?
Well, ideally speaking, we don't want this to grow, but then there are methods where it is allowed to grow in a sublinear. So, because they may possibly be able to achieve a better accuracy, and if that can be achieved, using slight improvement, slight increase in memory, like 3% or 5% increase in memory, that is still different.
So, for example, we did that for all the previous tasks, we just keep one example that's still growing linear, right? So, how do we get some linear in that case? Even if you store just one sample per class, it's still linear.
Linear in terms of
Tasks.
the thing is that this is not at all useful to it. So this storing one example is not going to help at all.
Yeah.
And so generally we say the linear in terms of the parameters. Right?
Okay.
If there are some parameters, the model has so a different situation is that you learn independently for each task. So when you learn independently for each task, you say the number of parameters that you have in your model is n.
Yes.
If there are k tasks, it becomes k ends. So that is kind of a linear. That is something we should be done. So we can grow the parameters. Maybe like for task 1 we have n, and then for task 2 we want to have some n plus say 10% of 1 times n. So task 2 again 0.197. That is something like we say that's a linear growth in parameters.
Add some parameters for each task. So, and we also say we add a number of parameters for each task. They can also a number of parameters based on.
So those also come.
So actually, is it possible to repeat the question so that everybody will get, because it is very low voice? Yeah.
What he's asking is that instead of adding the parameters, did you think of removing some parameters also as something is going to update? Yes, it is true. For instance, there are multi-based approaches very small amounts of data parameters that can be seen as some removing. They basically you say after you learn one task, one to find out important parameters, and you think of just removing those parameters from the model, or basically those parameters in the model. So that also can be seen as something that comes under this architecture based. Yeah, so we can just continue this work. Okay, so yeah, so generally having hyper networks. Yeah, so we can see this picture. Okay. Yeah. So generally we want to solve some tasks, and we have some model which could solve that as for example, if it is classification, can be a big word or can be some convolution or formation and or even resonance or transformers. So there could be this could be a network, some mean network, which will solve that task. And recently we have introduced something called hyper networks. So the hyper networks are something like a meta network which will be able to predict the parameters of this main network given some input. So the input could be something like some sort of a description of the task, or some sort of a description that can be a classification task or can be any task, but some descriptor describing that task or some representation of that task. And provided that representation of the task, and using that representation of the task as input, which is network, it could generate the parameters of the main network, which could solve this task. So there are now two networks. One is the main network here, which has some parameters say psi, which could solve this task of predicting input to output, and that parameters can be generated by some meta network, which can take some input E, which describes parameters. So this meta network is often known as the hyper network, and this can be used for several tasks, for instance, model compression or some pivot planning. Several of these problems, people have to use these hyper networks. And Now, what we do here, how we see how we can use this hypernetwork to solve these continual learning problems, and how we can come up with more effective hypernetworks which can solve the continual learning problem. So, generally, this is how the hypernetwork works. This is your main network. So, these are the weights at each layer, and you have a hypernetwork which will generate these weights given some representation of that. So this is how it is going to do for if we want to apply it for different tasks that we have. For task 1, you give some representation of task 1 and generate the parameters which will be helpful in solving the task 1. And for task 2, you give some representation of task 2. The hypernetwork will generate some parameters which will solve this task 2. Yeah. And if you look at the learning process involved with hypernetwork, so this is how it's going to differ compared to the normal learning process. In the standard learning process, you have your network with some parameter, and you have some loss function, and gradient-based updates where you update these parameters of this network. And in a hypernetwork-based learning, so what you will be updating will be the parameters of this hypernetwork. Right? So these loss function will be propagated back to update these parameters of this hypernetwork. And that hypernetwork is what is going to generate these weights. So you don't explicitly have that weights for this as a network. It is going to be a function of this, or it is something which is output by this hypernetwork. So you update the weights of the hypernetwork.
The meta-learning and continual learning is exactly meta-learning.
Generally, there is a small difference between meta-learning and continual learning. So, again, in meta-learning, you assume all the tasks are available. Assume that some k tasks are available at the time of training, and then you want to generalize some unseen task. So there is this assumption that if some number of tasks are available all at once at the time of training, again, in continual learning, there is not the assumption.
But this is a very similar architecture to a meta.
Yes, how we can adapt this architecture for continuous learning. Yeah, so if we just directly use this hypernetwork to generate all the weights, no, the hypernetwork so that a main network may have very large number of weights, and the output dimension of the hypernetwork is very high, and consequently the parameters that is associated with this hypernetwork is going to be very large, and then it is not going to bring much efficiency in terms of storage of the parameters. So what people have done is that they use something called hypernetwork, where they generate parameters in chunks. Instead of generating all these W1, W2, W3 all at once, they generate W1 first and then W2, W3, etc. Where this hypernetwork is now conditioned on something called RE, which is nothing but, for instance, some representation of the layer. Yeah, so that layer 1 can be represented using C1, layer 2 can be represented using C2, layer 3 can be represented using C3. And you provide that as an input to this hypernetwork and generate parameters for layer 1, then you generate parameters for layer 2. So that will make this hypernetwork more parameter efficient. The size of that is going to be very small. And now, for continual learning, or when you want to adapt it for different tasks, this hypernetwork can be conditioned on this task ID also. Like PT could represent the representation of some task. And if you condition this hypernetwork on this PT and then on C1 representing the chunk ID, you can generate the parameters corresponding to this layer and corresponding to this task. Right. So, yeah, so this is how you can see hypernetwork can use for multitasking, where you condition this hypernetwork with respect to the chunk ID as well as the task ID, and you can generate the task of parameters. So what we found that, okay, this assumption, so this makes an assumption that, okay, each of these parameters can be generated independently given this chunk ID. And that assumption is something too strict and it may not model the normal the networks that we typically use. So if you look at these networks, there could be some dependence between the base that is generated here and the base that is generated here. So it's not completely independent. So how we can capture this dependence between these weights that is being generated by this hypernetwork? That was the first question that we addressed. And to address that question, obviously, now you can think of each of these weights depending upon the previous weight, W2 depending upon the previous W1, W3 depending upon the W2. So you can think of there's some sort of a dependence between the which is not modeled with the standard hypernetwork, where they don't consider any sort of dependencies between these parameters that is being generated and this parameter that is being generated for each of these layers or each of these different. So we first try to address that, and we address that using a LSTM hypernetwork. And then we propose some novel regularization techniques to use these LSTM hypernetworks for a continual learning. So you can think of how this LSTM network is going to address this question. It is possibly very easy to see how it is going to address, because we know that LSTMs are capable of modeling the dependencies with the previous sequences or previous data, right? So we can think of an LSTM network here. So the LSTM network takes as input the task ID and then chunk ID. It generates the first set of parameters of the main network, right, corresponding to the first chunk. And then this LSTM will generate the second set of parameters, but it also takes into account the dependence with the previous set of parameters. So the LSTM can model that sequence data, right? The LSTM will be able to model that dependencies. So this LSTM network will take care of that issue that we found with the standard chunk hypernetworks, and it could generate parameters taking into account the dependencies with the previous parameters that has been generated. So this is how our hypernetwork is different. We use the LSTM hypernetwork, and you use it to generate these parameters for the main network. And now, how we can make this LSTM network to learn continuously without fault? And to achieve that, we use a regularization. So in this regularization, it's something similar to knowledge restoration. Okay, when you try to learn something for task T, you store what you have learned, the hypernetwork that you have learned for the task T-1, and the hypernetwork that you are currently learning for task T should be able to produce the same output as the hypernetwork that has been already been learned. So that is the basic idea, and that is also known as knowledge restoration. So this is the regularization technique which will prevent the hypernetwork to forget when it is being adapted to the new task, where this can be seen as the output of a hypernetwork that you have already trained just before training on task 2. And this is the hypernetwork that you are learning currently, and this should produce the same result as already learned hypernetwork. So that prevents forgetting. And we made some modification to this based upon the item. So if you look at this regularization, it says that all the parameters, all the mean parameters that is generated by this hypernetwork that is already learned, and all the mean network parameters generated by this hypernetwork that is we are already learning, they should exactly match. All the mean network parameters should exactly match. But then we know that some of these main network parameters are important for some tasks, and not all the main network parameters should exactly match. It can differ, while only those parameters which are important for the previous task should only exactly match, while those parameters which are not important for the previous task may not exactly match. So taking into account this, we came up with a regularization technique where we multiply this term with something called the Fisher information matrix. So the Fisher information matrix, to just what it is, it is some sort of a it's a matrix over the weight vector, and will be able to find out which weight vectors are important for any task. So it gives some sort of importance of weight for each of these different tasks. And we multiply this regularization with this spatial information matrix so that we maintain that only those important parameters that are important for previous tasks, they are maintained as it is. The rest of the parameters are allowed to deviate from what it is. So this gives a more flexible approach and flexible model which can adapt to the new task. So vectors is simply computed based upon the gradients that is already computed for your current assignment. So this is the loss function, and you compute the gradient of this with respect to the main network parameters, and we use that to form this spatial information matrix.
EWC task also taking elastic wave consideration.
So there, it is only based upon, this is directly based upon the parameters. If you compare this with EWC, you multiply the spatial information matrix directly with the parameters. Here we are multiplying with the parameters with like the output generated by the hyperlink.
As we keep on masking more parameters with the season tasks. So
Maybe I'll do one thing. I'll finish this and we'll take our questions also. Yeah. So this is one of the approaches that we propose. Then the other approach is based upon the network growth, where we added some for each task we maintain a separate set of parameters. So we made a so generally this idea comes from the multitask learning, where we maintain some shared parameters and task specific parameters. So here we found that okay, those parameters which are modeling the dependencies in an LSTM, we keep them to be same across the tasks, while the input specific parameters we keep them to be different for different tasks. So it's not like you'll be growing all the hypernetwork parameters, but you keep some of these hypernetwork parameters shared across all the tasks. That is the parameters which model the dependencies, while the input specific parameters that keep growing with respect to each task. So this is another approach that we. So in this approach, you don't need a regularization. You can just do a continual learning on hypernetwork just by adding some additional few parameters corresponding to this input, and that will take this or that will enable you to learn for new tasks without forgetting. And yeah, so again, as I said, we consider these three setups: the task incremental learning, domain incremental learning, and class incremental learning, and the experiments that we have conducted. So some of these results are here, and we found that this proposed model, the LSTM net, as well as LSTM net IWR, which is the important weighted regularization that we have proposed, and LSTM net grow based upon the parameter growth. So those performed much better than the baseline approaches like EWC, SI, online EWC, and previous hypernetwork based approaches. And yeah, we found this to be consistently getting better performance or all these different types of. These are the typical data sets that is used for checking the continual learning performance, like split and list, permuted and list, and one based upon CIFAR 10 and CIFAR 100, where you consider the first task to be CIFAR 10, and then you split the data of CIFAR 100 into some 5 different tasks, and totally you have 6 tasks, and you see how the performance is. Yeah, so these are some of the results that we have based upon this hypernetwork based approach. Yeah, so we found that okay, important weighted regularization is quite useful for improving the performance of continual learning. It will give the best performance, but that has a disadvantage that is like additional increasing parameters for every new task. Yeah, so so coming to some of the future work for continual learning. So most of these approaches are assuming some task ideas available to you, but that may not be the case for me. You may not have a set task idea available to you, and it is like a task agnostic setting as well as there are, the task boundaries are also not many practical applications. For instance, if you look at social media, you get keyboard that data keeps on coming, and there will be some changing distribution of data happen at some point of time, and you may have to identify that and adapt your model. So how to come up with continual learning techniques when you don't when the task changes, when you don't have the task ID, when task boundaries are not covered. That is one of the future directives. Then next, streaming setup. For instance, in all these models and all these setups, we assume that when you solve a particular task, all the data from that task is available to you. But how about for each task also, when you look at the data from a task, it is coming in online fashion, in a streaming setup. How do we develop continual learning techniques for such cases? So these are some of the future directions one can look at. And yeah, so continual learning is also known as lifelong learning. You may often come across this name also, lifelong learning. It's same as continual learning or incremental learning. When these are different, these paradigms, these machine learning paradigms are different from continual learning, like multitask learning, transfer learning, domain adaptation, or meta learning. So there is having a lot of interest in continual learning in recent years, and there are so many papers which has been published continual learning in recent. There's a lot of interest, and there are many papers coming up in continual learning. For instance, you can see the number of papers on continual learning is keeping on increasing recently, and proportion of papers on continual learning is also increasing in the recent years. And there is also a conference which has been started on continual learning. It's known as First Conference on Lifelong Learning Agents, which covers all these different paradigms, also not only continual learning, but all these different paradigms also. And first one, which happened just 2 months back. So that's another progress happening in this future. And if you're interested in using continual learning, there is also a library which is known as Avalanche, which doesn't have all the techniques, but actually some of the techniques have been outlined there. And here are a few of the references. So maybe I will just take one question and the next topic, 3 o'clock, right?
If they have questions, they can.
I have the rest of the questions.
So the piece which I was asking was that as we keep on masking parameters, as we keep on tasks, is there any relation between how many parameters are masked as tasks? And for example, is the number of parameters masked the same with each task, or the first task has the most number of parameters from the second?
You can keep on waiting. Most of the time that is determined using this visual information methods, which can give you some importance of parameters. That keep on waiting to close the task. And that may not be so when you have a large number of tasks, you may not be able to approach those. Because you may run out of the parameters. You may have to also have a network growth also which has more parameters. So maybe coming back to the methodology, most of these different techniques are based upon hybrid approaches where people combine all these different methodologies to come up with something small. So then, we will take the questions offline.
So we are very grateful for your time. And thank you for sharing your thoughts and experience to us. And your talk is very relatable to each and every student in the class. And anyhow, they will be contacting you offline if there is any doubts.
Please feel free to contact them.
Thank you so much, sir.
Yeah. Thank you, sir. Thank you. Thank you, sir. So now what? Next what? Give it. ఇప్పుడేనా నెక్స్ట్ బ్రేక్ ఓకే ఆయన ఆన్లైన్ ఇస్తారు కష్టం వస్తుంది లాస్ట్ ట్రాక్ కదా పాపం ఇంతవరకు వెయిట్ చేయాలి వచ్చి హాలిడే కదా సరేనండి ఈరోజు డైలాగ్
Screen sharing.
CH 1103. Yeah.
Yeah.
వాళ్ళు Hyundai Mobis వాళ్ళు Hyundai Mobis వాళ్ళు అయితే వర్క్షాప్ పిలిచారు 19th నేను ఉంటాను 19th నాట్ అవైలబుల్
అంటే వాళ్ళ మెమరీ అట్లా వచ్చేది
అవునవును విష్ణుకి ఐఎమ్ నాట్ అవైలబుల్ whether if you can postpone to some other day. Huh? And I'm not there. నేను Hyundai Mobis వాళ్ళు పిలిచారు కదా నేను చూసుకోలేదు ఇప్పుడే చూసుకుంటాను నేను లేను ఐఎమ్ నాట్ దేర్
ఓకే
యూ వాంట్ యూ కెన్ గో బట్ యూ టెల్ మాట్లాడు ఎవరు శరత్ ఐఎమ్ నాట్ అవైలబుల్ అందండి నేను ఇప్పుడే చూసుకుంటున్నాను చెక్ అది చెప్తాను దెన్ యూ కెన్ ఆస్క్ దెమ్ చెప్పు నీకు లేనని ఓకే అంటే
So I take privilege in introducing our speaker today, like Professor Dinesh Singh. Dinesh Singh is an assistant professor in the Department of Computer Science and Engineering at IIT Mandi. Dinesh Singh completed his PhD degree in computer science from IIT Hyderabad under the supervision of Professor C. Krishnamohan. He received his MTech degree in computer engineering from NIT Surat. Prior to joining IIT Mandi, he was working as a postdoctoral researcher with Professor Akato Yamada at Riken Center for Advanced Intelligence Project, Kyoto University Office at Japan. His research interests include machine learning and computer vision. His research work has been published in reputed journals and prestigious conferences including pattern recognition, IEEE TKDE, IEEE transactions of big data, IEEE TITS, BMVC, IJCNN, IEEE CEC, and IEEE Big Data. He volunteered at several national and international conferences. He also served as a PC member for IEEE Big Data 2018. He is consistently providing reviewing services at top venues in machine learning and computer vision, including PAMI, MLJ, TIP, TITS, PR, CVPR, ECCV, ICML, and URIS. He is going to deliver a talk on NICE, a Newton for stochastic optimization. Thank you so much, sir, for your presence here.
the introduction and thank you for the invitation. So today I'm going to talk on one of my recent work, that is strong approximated curvature for stochastic optimization. So generally, like we all work in AI field, and once we formulate our problem, so finally we are going to need a optimizer how to achieve that objective. Okay. Although like little away from the ML, it's part of optimization. That is completely different domain. And generally nowadays the data is growing, but so that's why the batch-wise processing is not an option. So that's why we choose for stochastic optimization, where we can train online models, or we can pick suitable univariate size, and then we can optimize the things. So if we go forward, like this is the common objective function, which we got like empirical risk minimization. We define some loss function over the predicted output and the target value, and that's the information we have through which we are going to optimize the parameter W. That what will be the optimal value of W. That's all our objective here. So now, depending on the what type of functions we are using in this one, like it would be like regularize hinge loss function, or it could be logistic regression, or any other function, including that. So once we have the target predicted value and target values, then we define this one. So now there are different type of functions are available. We are convex, we are non-convex, continuous, and non-continuous. So although the method or algorithm I'm going to present, that is applicable, but for theoretical analysis, we make some assumption on this function, and that this function should be strongly convex and twice continuous differentiable, as we are going to apply the curvature in convex, which is Hessian, means it should be twice differentiable. And then, of course, we are also considering the regularized version, so that because like Newton method. So in Newton method, we need to invert the Hessian, and for that we need to install the full range of Hessian. So using a regularized will keep make us ensure that. So now if we come how we achieve this objective, the first algorithm comes in our mind is that's STD, because that's the most simple and most efficient algorithm. But this is works based on the first order information. So we calculate the derivatives or gradient of the function, and then using a suitable step size, we update our parameters. So that is like very old algorithms invented in 1951 by Robinson. So this has benefits. So even like when we are talking about deep learning, so everywhere mostly we are using STD or its few variants like SVR, where we just reduce the variance. Sometimes during stochastic optimization, it might fluctuate. Just to reduce those fluctuations, so we reduce the variance in the gradient, and then we can update it. Then there are so many other variants using momentum and scaling of the error based on that, so that we can get that one. But still, this first order based methods are our first choice, because computing and storing gradient is very, very efficient. But using SED, actually, when we talk about from the theoretical point of view, so yes, there is no guarantee that we can converge to the optimal solution at the end. and number of iterations required to reach the optimal is very, very large sometimes. Okay. So that's the problem. Now, when we are coming to the second order method, so then Newton's method is the we use the full Hessian, its inverse, and then gradient. But here comes the one part that computing and storing and inverting all these Hessian and all these three operations are very, very computation intensive. So need a lot of space. So let's say nowadays ResNet 18 models, everyone is familiar and they are training it. But if we want to use Newton's method for 18 models, so ResNet model is 7 million parameters. So then the size of the Hessian that will be 11 million plus 11 million. That big matrix. Okay, so none of the world's largest supercomputer has that much memory to store this matrix for the deep case. So Newton's method cannot be applied for the deep learning cases. So although this Newton's method is very popular when we are coming to the second network or like logistic regression type of problem, where number of parameters are larger than the number of dimensions in our data. But when we talk about deep learning, the number of parameters are much larger than the dimension of the data, and that's why there are not many parameters to train. So Hessian is very, very big. So not only storing, even the computation is a problem. Then, of course, for large matrix, inverse itself is complexity in the order of cubic. So this is the most horrible part. So, but the good part is that when we see the carries related to Newton's method, like for logistic regression, if we properly normalize the data and other things, so it guarantees that within a single update, we can reach to the optimal value. So we need not to train it for so many iterations. Single iteration is efficient. So that's the good part of that. So in order to achieve this object, obviously this object is difficult, but there are certain methods through which we can at least try to approximate this Hessian, and then we can use it with the gradient to get the more guided updates towards the optimal. So here the best class is the Paschen-Newton method. So there are several methods. When people face this problem, so they started exploring that instead of computing this entire Hessian from the scratch, can we come up with some idea that as we update the weights, similarly we can also update the Hessian using the only current information what we have at hand and the previous Hessian. So then they derived the name is scale equation. That's the one equation based on that all those methods comes under Paschen are formed. And idea that finally this Hessian is once this W is updated, then the difference between the current W and the previous W, that was the update. Then by using that into the Taylor equation, so they come out that okay, so the new gradient equal to the old gradient plus beta times the difference between those weights. So that's the one thing. So but now this is the vector, then matrix, and then vector. So in this case, we can get those vectors. But when we are trying to get a matrix using the vector operations, that only we can get up to one rank. So, but using this one rank update over certain times, using some initially invertible matrix, like in practice they use like identity matrix. So identity matrix is a full rank matrix and invertible. So then they started updating over that using this one vector update. finally they get. So then there are VFGS is there, which trace all the updates for the iterations and finally get us the current this Hessian. And also just to reduce this computational complexity associated with the inverse. So because inverse of the identity is inverse itself, that instead of first updating and then inverting, then they directly solve this few steps of linear algebra and using this inverse identity to directly estimate the inverse of the Hessian. So finally, here there is no inverse. So this approximate Hessian is the like directly the inverse of the Hessian. So that is there. But again, here all the information we use that is very very old. So now based on the very very old information we are trying. So at least till the back step we are sure we can approximate it very well. But and again. There is actually no true this Hessian or second order information is computed ever. Just it's an approximation from the history. Then recently for deep learning, especially this KPS, so machine learning methods they work well with the logistic regression and but when coming to the deep models, they are not performing in practice. So for deep learning, so few years back, this KPS optimizer was proposed, where they under certain assumption that their loss function is the probabilistic loss function. In such case, the Fisher information, which is like expectation of the outer product of the gradient. So this is equivalent to the Hessian. So actually, if we have the gradient, we need not to compute the Hessian, but only in certain cases. So then, by using the underlying this architecture or the processing of the forward pass, they again come up with the fact that this Hessian approximation, how they can get. Across the layers, they don't need to compute it. So within the layer only they can compute. So because there are large number of layers, so finally lot of off-diagonal information they need not to compute. So they are not computing that. Only within the layer Fisher information they are computing. Then again, this Fisher information is the Kronecker product of two very very small matrix, which are like activations and this one a derivative of that those activations. So those using those two informations, actually when they perform Kronecker, that's exactly equivalent to the Fisher within that layer. And then over that again expectation is a problem. So if we are going to compute the expectation, we need to store all the gradients. Then again, it needs a lot of memory as well as computation. So instead of going with the sample by sample average, so they just took the average or expectation over the average of within the mini batch, then average over that one. So doing that, they are also very good. If I can say that this is the state of the art method. So just to, if we want to employ arbitrary information within the deep learning methods. But still, there are limited case to probabilistic loss only. And another is that again there is too much approximations. So finally, the gain when we are optimizing is very limited, not much far from the SDD like first order information. So how we can improve and how we can avoid that we, for any generic loss function we can go with the this Hessian based or second order methods. So and instead of using all the approximated information, let's if we compute a little bit of the actual second order information, and based on that, we can estimate uh, the entire history. So that's like my practice here. So now coming to the preliminary methods. So Nistrom method is very popular in kernel-based learning. So when we encountered a large kernel matrix, then again same problem is there. Kernel matrices are also like square matrix and square and symmetric matrix, and again need a lot of memory. So there are numerous approximations exist for kernel methods. So this Nistrom method is one method how we can avoid the storing and computation of the entire kernel matrix. So the similarity between Hessian and kernel is that both are like the symmetric PHP matrix. So now just now give a brief what is Nistrom approximation is. So let's give a matrix H, which is the D cross D matrix, and we know that it has maybe full rank or maybe low rank under PHP assumptions. So, but we want to just approximate the K rank of this matrix. So, what is the best way to get the K rank approximation? Then we can apply SVD over this matrix H, and we can get that K rank approximation. And mathematically, that is the best K rank approximation. But again, the part is if we cannot compute and store this matrix X, then we cannot apply SVD at all on that one. And then again, computation of SVD again is in cubic. So there is no gain if you want to apply SVD. So how Nistrom approximation actually do? So instead of computing the entire Hessian, they actually compute only few columns. So few columns means the kernel distance between all points to only few points, and that is represented by this column matrix C. So let's say if we are selecting M columns, so the size of the C will be our D cross M. Only that much information we need to compute. Then this M is actually the kernel distances between those M points to those. So basically, M is the subset of C. So we need not to compute M, we need to sample C. Then this M is a very small matrix like M cross M, and now we have the control over the M. So larger the M we are taking, so we are ensuring much better rank. If lesser we are taking, so less is our rank, because our rank is upper bounded by M. It could be less than, but not more than M if we are picking M columns. So once we have this very small matrix, we can apply SVD. So once we apply SVD, then we get the K and sigma K, UK. So that is the best K projections of. Then just if we simply solve this, here is the pseudo inverse because it would be low rank, so perfect inverse may not be possible. So, but then this inverse goes to this one because you are orthogonal matrix. So finally, if we just take the square root of the sigma, this is nothing a diagonal matrix, and only those are positive values in the SVD, so we can take a square root. So in this way, finally, this matrix we can come up with two identical parts. So that is Z and transpose. So Z again, Z column matrix, which is D cross K, where K is our rank, which is at max M. So finally, at any large matrix H, which is D cross D, we can store only one part there cross M. So only that much memory we need, and we get compute. Now, instead of just using X for well, directly storing it, we can use share wherever we need it, and we can do our. So this is like very very powerful method. Maybe 10 years back, and widely used in kernel based learning. So just to give a like picture presentation. So let's say this is our entire matrix X. So here only the blue part are those columns we are computing. Then if we collect them, so this is our C matrix. Then the same indices, column indices what we pick, the same indices we pick. So we get our N matrix. We can apply SVD because this is very very small matrix. Then we get our parameters, and by projecting our column C or these things, we get Z. So doing Z transform will give us approximate X. But we need not to directly compute or store information, only this information we need, and using this information we can do our operation. So same techniques like I applied for approximation of the Hessian, because there are similarity. Hessian is also symmetric and asymmetric. At least like under convex cases, but if it's non-convex, not guaranteed because shadow points are also there. So there the matrix is indefinite. Okay, so just an illustration how the quality of approximation is. Like this is the Hessian matrix for logistic regression after few epochs, and this is adult data set, which has around 300 attributes. So 300 parameters in our page. So Hessian will be 300 plus 300, and it looks like that. Then we simply compute only 10 columns. So using those 10 columns, we approximate. So we can see that the matrix is very very similar to this one when we are using only 10 columns. Then if we talk about like what are the theoretical guarantees that how much these two metrics, the approximated and original, can deviate. So there are good theoretical guarantees are there. There is a upper bound. So let's say if we have the best k-rank approximation of H, what we can get using SPD. So this much error will be definitely there. Does not matter what method you apply. So then this is the one case that on top of that, then only the diagonal entry. So our error is upper bounded by the square and the trace of that parameter. So it's when theoretical guarantees are there, how much data we need and how much samples, so that we will keep there. So in this way, this Nystrom method is very very good candidate to apply for just to approximate the Hessian. So now when we are coming to the update of Hessian, so this is the update rule. So we need Hessian inverse and the gradient, and that's the gradient directly in case of SVD. If we are applying other kind of methods also, so for computing the gradient or just to apply some momentum. So then this is the finally the first order information what we can say. Then we use H inverse as the preconditional to transform B, and then we update those parameters. Now we already get checked how one can compute a like sketch of the Z part even Hessian pattern by only computing M columns. So now this is the part. So if we extend that one, let's say this is our approximated information. But now comes the part. If N is the definite matrix, we can invert it. But now it's a low rank matrix, we cannot invert it. So in order to make it invertible, so we need to use some regularization provide, and then it is invertible. Then by using first order information, we just get it. But if we directly compute this one, again, we need to store this h, approximate h, and then again inverse part is there. But here the like if we see that h is z trans and then inverse, that's the straightforward way. Now we have this Sarman Warshad-Goodwin formula. Just to avoid not to compute those things directly, we simply solve this and we come up to this this form. In this form, the good part is that neither we need to store any D cross T matrix, and neither nowhere there is a part where so our computation is. So only big part is that is IAK plus JJ transpose inverse. So, but if we say that this is a K cross K matrix, so which is very small, like 10 cross 10, previous example, same Z transpose Z, then again that is K cross K. So finally, just inverting this part is easy, then by using all those parts, we can compute. So even if we take this much part, we recompute this one, then during the stochastic update, we only need to compute this part. So Q part is maybe from the angle. So let's say this is the SPDL right now. So if simply this is the gradient, and if you directly apply, so this is gradient. But now we wanted to use Newton's type update. So we already computed this C part quickly using only M columns and compute our chat condition. We computed this part because this Hessian generally in stochastic we compute at certain intervals, or maybe like in this case, in our case we computed at the beginning of each epoch, but during the iterations of maybe sample wise or maybe mini batch wise, then in the we are updating. So here we simply use this pre-computed Q, and here those are pre-computed one, and then we simply solve this one. Then within very small computation, we can get this. So now this approximation is like generally need not to be applied when SDO you can apply with any first order method. So only we need these two variables to be computed, and then we can apply. So similarly, like SPRG. So SPRG first compute a global gradient for the previous model. Then for the current model, for a particular mini batch, it computes the gradient on the current models and the previous epochs models, and then average. In this way, it is able to eliminate any sudden fluctuations in the gradient, and finally it reduces the overall variance. And in certain cases, it converges or perform better than SCD. So although like we need to store two models and twice we need to compute the gradient, so that's a little computer part, but that's the internal algorithm of the SCR. Then again within the same settings, within the first order variance gradient, we can directly employ this way, and that is about approximate Hessian, we can say. Okay, so now coming to the computational complexity. As first of all, we are not for the Newton, it requires D square n, where n is the number of samples and D are the number of parameters. So in case of logistics, the number of parameters and dimension of the data is same. So it's D square n, just to compute the Hessian. Then to invert, we further create DQ. So D square n plus DQ for inverse, that is our thing. And D square is our memory, which is like again the problem. While coming to our this additional based approximated Hessian, we only need to compute this M column. So that is D by DA plus finally, after the year approximation, our n shrink k, and that is the part of z. The only thing you need to store z, so this is d and k, which is much less than the d square. And again, the entire part for computation, that is also like much less than the dq. So now coming, so whether this approximation is leading us towards optimal, or means our model is finally converging or not. So under certain assumptions, like I said previously, so we are going to compute second order information. So we need to assume that it's twice continuous differentiable. So method is applicable for convex and non-convex of these. But let's show the convergence, we use the convex settings. So we also assume that the f is convex. So then again, we assume that there are this Hessian is our function. Using at least the regularized case, we can say that it's using the smallest eigen value and the largest eigen value. Apart from that, and then simple discrete continuity. That is, and all these settings are like very common when we are driving convergence for this convex cases. And based on the assumption two, we also come up that again our method under the regularization parameter, this should be greater than 0. Then our this is also upper bound. Using this assumption and lemma, we are able to do the quadratic convergence of the Mistrom SPD, which is like slightly better than the linear convergence of the SGD. So here we have the guarded part. So finally, our method should converge faster than SGD. Similarly, for SVRG, so for SVRG, we at least able to prove the linear convergence under certain assumptions. Now coming, so far we handle the dimensionality of the data, but or the number of parameters we are learning. But now again, the Hessian is like d square and is the computation part. If n is very large, then again this computation is huge. So and as we are applying this stochastic updates, so even computing C part sometimes becomes computationally challenging under large data settings. So how we can avoid? So this is just a type of heuristics. So instead of using the entire data, we prepare we are taking some subsample of the data just to compute this C. So this in terms of this one, so this comes under the subsample methods class. So where instead of using the entire data, we are just sampling using those points, we are estimating the hash. But one thing we can obviously go for random case, but if dimensionality of the data is also gone, so sometimes there is enough deviations in the data just to avoid that deviations. So we simply come up with this heuristic pattern, which is like distribution preserving subsampling, where we separate the classes and then perform KB clustering over individual class, and then we get certain cluster in each class. Then each cluster of each class we equally distribute among m such partitions. So now, whenever we are updating, okay. So in this part, so when we are computing C, so instead of computing it from all the same parts, obviously we are computing only n columns, but those n columns we initially compute from all the same parts. that is also again very complex. So we use this TPP samples, and we again do the sample. See, in this way, in case of very large data sets, so we can also further reduce the complexity arise into the data. So, and now instead of using one way is that we can keep using only one sample, because one sample under generated by this distribution preserving sampling has similar statistical property as of the original data. But still there is a difference among the different partitions. So just to also incorporate that, so at every report we use that one samples, and after the end, then again we start in the round robin fashion. So every time we incorporate. So finally, maybe after let's say we make P partitions. So maybe after P part, we completely incorporate all the data into our learning process. So this is the how the data looks like after those are generated by this. Like this is the PCA projection of real sim data set, which have around 22,000 dimensions. When dimensions are large, so usually the data lies or the axis or near to the horizon. But even our subsamples are very similar to each other, and also very they are, if we consider their mean and extent other properties, they are very similar to the original data. So that's there. Just to give you how efficient it perform numerical, we compute numerical experiment with several data sets with L2 logistic regression and L2 SVM and cross entropy less loss, especially for deep neural network. So this is the setting of hyperparameters, and we compare with the existing Bayesian neural methods and first order method we use. And for deep learning, of course, we also compare with K. So if we see that for logistic regression, with only 2 columns, we are actually computing in the Hessian. So here is like an SVR, that's Nistrom approximated SVR, and then with the D is under the subsampling case. So subsampling, because the data is less, so the time process, how fast it reduces the error, or how fast it reaches near to the optimal. So with less data, given less data, the Marikov gain maybe it is less, but like time wise it is much efficient, and with the when we apply this method, so the optical means error for the rate of the reduction in the error is very fast in comparison to the Bayesian neural method. While we started from a very efficient point, so adapt would not perform much better, because we are very near to the optimal. So we can say that even after reaching to the near to the optimal, then there is no further progress in the method. While the second order information can still much beyond that point. So, and the trend is also followed in the validation decreasing. So it's not only like we are overfitting the models, but model is like well characterized. So this is the one data set. This is relatively very high dimension. With other data sets like SIPR and others, so again our methods perform consistently better than this one, both in during optimization with the trained data and with the validation part. Again with the several other data sets. So all these results are for logistic regression. Now coming to the L2 SVM. So again, when we change the loss function, so still our this method performing better better than or even sometimes comparable. What this this resident 152, it has means millions of parameters. So for me, it's very difficult. We cannot apply Newton's method at all. So, but our this approximated method and the existing K-FAC method. If we see the performance, the K-FAC is efficient, obviously computationally, but the error is no much better than the S3. It's almost same in this one. Even when we change the model, these two models were trying to the mainland, the settings were the same for all the vectors. And in both the models, like our IN-SSCOM S3 is performing much faster than the. And not only in reducing the optimization error, also the test accuracy we see, so is better than this one. And in the early hypothesis, it always has the lead over the SVD and K-FAC. So in this way, we can conclude here. So our Hessian approximation is much efficient than the K-FAC, and obviously using curvature is better than the one is first order information. So now just coming to the part, of course, we cannot apply this method for entire training of the data, but transfer learning is one way where actually we use pre-trained models. We can say that the model and the parameters, what we can consider when we are so we are already on a some initial point. Now from there we need to actually optimize. But the problem is that in transfer learning we do not have enough data to train this one. So generally people train only the top layers only, while these bottom layers are considered as secondary. So in this case, if we use second order information, that gives us a very good results. So here there is one such problem where we need to classify which MRI image has tumor and which do not have tumor. So under that one, we use densnet to generate the feature. That means simply using logistic cross function. This Newton methods, of course, our method we can apply, but Newton we cannot apply for clarify deep models. So, so just to be compared, so how good our approximations is working in comparison to the Newton. So, in comparison to Newton, if we see that the first order information also after certain process can achieve the same performance. But using this curvature information of the Newton method, we achieve that same performance only in 3 blocks. So even our approximate information follows very closely the Newton's way. So we can say that even for these models of this kind of thing. So using the second order information is much likely. So in this talk, I present this nice.
No, basically, what kind of data? Okay. So this is more suitable method is.
So this is like methods. Any kind of data we can apply.
No, is it for some sort of temporal data or what kind of data it is more suitable?
I don't know in this case because this is purely the optimization
applications one can think of when using this.
Yeah, so obviously, as I said, in transfer learning, where we have very limited data, but still we want to reach to the optimal without fluctuating too much. If we use the first order information, So it's generally fluctuates, and only after certain points we can reach till that objective. So although that data is not a problem because this is optimization process. So whatever data is there, we have the error and a objective to achieve. So it's just that part. So mostly like when we are working with machine learning, so then we see that what is the best objective and what is the best formulation of, that we can use. So that's there. So this method is once we decide that what is our objective function, so it's just a matter to achieve that objective. So it's free from like data, but obviously data effect, like if we have a very less data. Now, as I said that this Hessian is very large, trusty. So in order to make it full rank, we need enough data. But if we have very less data, so anyway, our Hessian is very low rank. So better applying low rank approximation is good. So efficiency, while our method is comparable or better than questioning methods, and even performance-wise, it's definitely better than cross product, and again performing better than the questioning methods, also even better than give for deep learning safety.
So is it published? This work is already published. Huh?
In the deep learning, can you go to the ResNet slide? ResNet and efficient net. Yeah, this one. So on efficient net, how did you consider the dimensions and how did you apply the approximation for efficient net?
Okay. So in this one, so this is imaginary data with that standard format to post from 24 and 3 channels that we go. So that's the our dimensionality of that data, but that's not directly associated with that our approximation. So we need to deal with the model parameters, the gradient, and then second order gradient. So like in logistic regression, the good part is we already know the formula of the Hessian. So just by applying that, we can get. But for deep learning case, we don't have that. So we need to go through that back propagation process to get the first order information. Then again, we need to back propagate to get second order information. So as even deep learning libraries don't use any formula to compute either gradient or this one. So instead we apply this.
Parameters are not fixed, right? Number of parameters for the deep learning tools is sometimes not fixed. For the parameters
Inside the model,
inside the model.
so once you decided your model, then the number of parameters are fixed. But what are those parameters? That's our objective.
Yeah, for which approximation?
So in that case, just we need to back propagate twice. Once with the objective, once with the gradient. So then we get this second order information. So although it's a little tricky, so you pass one time, so your model is kind of replicated. Like for first propagation, you get like if you have n parameters in the model, so gradient results of n parameters. Then again you get the another column that's also n. So each time the model is repeated. So let's say we that's why we could not pick more than 10 columns. So if we go more columns, we are much better, right? But with 10, it's kind of a replication of ResNet model 10 times in the GPU, and finally our menus will. So that's another thing.
We'll take the questions offline. Okay, we'll repeat it. Okay.
Thank you, Mr. for your talk, and congratulations for getting selected into active learning. And we are very happy as you are our alumni. Practice and momentum of IIT list so that we have memory too.
Hello, anybody there? Raghu? Hello. Hello. Hello, is anybody there? Hello, is anybody there? Hello. Hello.
Hello, sir. Hello, sir.
Hi. No, I just wanted to check. When are we reconvening? At 4:15 only, right?
Yes, it's at 4:15 only, sir.
Sure. Yeah.
Sir, reading, sir. Hello, sir.
Hi, Raghu.
సార్ ప్రెసెంటేషన్ కావాలంటే ఒకసారి షేర్ చేయండి.
Sorry.
పీపీటీ కావాలంటే ఒకసారి షేర్ చేయండి సార్. ఓకే.
Sorry. వస్తుందా?
ఓకే సార్. కమింగ్.
Okay, just 1 second. Let me see if I can make it full screen. Present and slideshow. Okay, good.
Hello, Professor Rao.
Hello, Professor Mohan. Krishna Mohan.
Yeah, good evening.
Good evening, good evening.
So, welcome back after the tea break. So, gives me immense pleasure to invite Professor Panduranga Rao and try to give a brief biography. He has given two brief, so I will take more. I will add more, So, Professor Rao Panduranga Rao received his MTech from IIT Warangal, that is earlier it was NIT Warangal, and MTech from IIT Kanpur, and PhD from IISc Bangalore. His research interests are in quantum computing and communication and formal methods. So, he is expert in the area of quantum computing, formula optimization. To tell he's the founder member of IIT Hyderabad Department of Computer Science and Engineering. So I welcome you, Professor Rao, for this workshop, and thank you very much for accepting our invitation.
Thank you.
So, give Professor Rao a big round of applause.
Thank you.
So now the floor is Professor Rao's request Professor Rao to deliver the talk.
Sure. Am I audible?
Yes, sir.
Oh, great. Thank you. Thank you, Professor Krishna Mohan, for the very kind introduction. So let me go on to. Are my slides also visible on the board out there?
Yes, sir. Visible, sir.
Okay. Thank you. Thank you. First of all, I'm sorry not to be there physically. I was not well, so I thought, why increase? Why increase the chances of contamination if I come there and so on? So yeah, sorry. I would have really loved to be there, but I thought I'll stay back and give online lecture. So initially my idea was to basically talk about our work. If time permits, I'll still do that. The work that we are doing at IIT Hyderabad in this area, at the CS department in this area. But looking at the nature of the workshop and this thing, I thought I'll first I'll actually start. In fact, a majority of this talk would probably be on as more like a tutorial on quantum approaches to combinatorial optimization. So it's a gentle introduction to this area is what I'm hoping to give. So at any point, if my audio has a problem, or if you want to ask a question, please feel free to do that. And I request the coordinator there to uh, pause me and ask the question. Okay. So all right. So let's go to the first slide. So this is the outline of the talk. What I'll do is I'll start off with what I will call a circuit-based quantum computing, which is now really a classic in the sense uh, it has been around for a long while, maybe 3 decades now, and that's why I'm calling it classic. It's a circuit-based quantum computing paradigm. And then we look at what are called Hamiltonians, which are integral to these circuit-based quantum computing also. But we will have a slightly different perspective, a slightly different paradigm that evolves by just looking at the Hamiltonians. We'll see what Hamiltonians are in due course. And the objects of interest to us will be these lowest eigenvalues of these Hamiltonian operators and their corresponding eigenstates. We'll see why they are important. And the reason why they are important is that they help us in solving combinatorial optimization problems. And so such quantum approaches to solve combinatorial optimization problems are what are called as adiabatic quantum algorithms. We'll look at that in some detail. And then we'll end up with a passing comment on a newly in the sense it's been probably around for about less than a decade, what are called as quantum adiabatic optimization algorithm. So there, so we'll look at that in due course. So the circuit model is typically this. I mean, I will okay. So my introduction to the circuit model will be rather fast because we'll just go to the level of what a popular science article would probably, and many of you might probably already be aware of this part. But I'll go to the depth of just a high level overview of the depth of let's say a popular science article and so on. So the quantum computing, if you probably have heard of, is that the fundamental unit of a quantum computer, just like for classical computers you have a bit, you have qubits for quantum computers, right? So that is something you might have heard several times, right? Then these qubits basically undergo what are called are subject to some things which are called gates, which are actually something called unitary gates. We'll look at what these unitary gates are shortly. And then what you do is, after subjecting them to some gates, you do some measurements, right? And then from the outcome of this measurement, you do some inference. You figure out whether you have solved the problem or not, and so on. So this is generally how the quantum quantum computing setup looks like. We'll go one slide each. We'll go into each of these so that we are on the same footing. So what is a qubit, as I just mentioned, is the quantum equivalent of a classical bit, right? So you have classical bits which are 0 or 1. A qubit is basically the quantum equivalent of the classical bit. How do you describe those things? If you have n qubits, right, where n is anything greater than or equal to 1, right? So you have n, 1 qubit, 2 qubits, 3 qubits, and so on. We associate what is called as a 2 to the n dimensional Hilbert space. Okay, and a Hilbert space is nothing but an inner product space with it's a vector space which is endowed with an inner product, and over the class or over the field of complex numbers, right? So that's about it. I mean, there's just a fancy name for the purpose of this talk, right? So a quantum state vector, which is a ray or a unit dimensional vector in this particular space, right? That's what is called as a quantum state vector. So if you write it more formally or mathematically, this is how you write it. These are what are called as kets, okay, which is basically a vector. So in usually we are accustomed to writing v and above arrow for a vector, right? V arrow for a vector. For historical reasons, we'll use this notation, which is a vector, which is actually a linear combination of which is a linear combination of these basis vectors, right? They're drawn for the basis vectors, which a basis for this particular 2 to the power n dimensional Hilbert space. So linear combination, and what are the coefficients? Their coefficients are complex numbers. Okay, and we have one more additional requirement, that the mod squared, if you look at the sum of all the mod squared of these coefficients, they should sum to 1, right? So mod alpha I squared for all the coefficients, if you take the sum like this, it should be actually 1. Okay, so that's and if you just look at this is for n qubits, 2 to the power n dimensional Hilbert space, etc. If n is equal to 1, you will see that it is actually alpha of 0 plus beta of 1, just one this thing, right? So that's a single qubit, case of a single qubit. Right now, this basically forms a quantum computer, so to speak, at a very high level, at a very abstract level. This is what a quantum computer is basically. I mean, if you have a bunch of collection of qubits and you do various things, which is the equivalent of doing some computational transforms on your classical computer. This you have to do certain dynamical things which map onto the notion of computation. So how the computer is made to, how the quantum computer is made to evolve is actually given by the Schrödinger equation, which is a differential equation of this type. You see that how the state evolves over time is basically is given by this particular equation. Okay, this particular differential equation. This particular thing, which quantity which I've written h is basically an extremely important quantity object which we'll be using for the rest of this talk. Okay, this h is basically called as is called a Hamiltonian of the system, right? What is a Hamiltonian? What is this differential equation? What does it look like? We'll not worry about it at this point. As we go along in the slides, hopefully a clearer picture will emerge. But suffice it to say that this is what is called as a matrix, which is actually an operator. Technically, it's called as an operator. You can imagine this to, once you fix a basis for the Hilbert space, you can imagine this to be a matrix that can be that is defined with respect to that basis. So this is basically, think of this as a matrix. Okay. So now what happens is, to cut a long story short, if you solve this differential equation, what you get is this, something like this, right? The system evolves from T0 to T1, then this is what you get. Okay, so this was your, is my cursor visible, my mouse pointer?
Yes, sir.
Okay, thank you. So if this is the initial state of the system, what happens is it basically gets transformed to another state, right? And the way it is transformed, so this state is basically, as you can imagine this to be a column vector, and this is therefore also a column vector. So therefore this basically is, you can imagine this to be a matrix of some sort, right? This is actually what is called as this operator, and once you fix a basis, you're actually talking about the matrix itself. So this is called, this whole thing, right? E to the power minus h t1 minus t0 is what is called as a unitary matrix, unitary operator. Okay, so as effectively what you're saying is here that your computation is basically evolving the system from this site t0, one particular quantum state, to site t1 through this unitary. You apply these unitary transformations, like just like for randomized algorithms. Those who are familiar with randomized algorithms, you would see that, or even Markov chains, etc. You would see that there are these stochastic matrices that are applied on distributions, right? Similarly, you can imagine this to be a unitary. This unitary operator to be a matrix that is being applied on this thing. The one property of this unitary operator is that the adjoint of this is, if you write it as U dagger, so U dagger U is the same as U dagger is the same as the identity matrix. Okay. Essentially, this means that it preserves the norm of in fact, it preserves the inner product. So if the inner product of two vectors was a certain quantity, after application of the unitary transformation on these vectors, the inner product continues to remain the same. One consequence of that is that it preserves the norm of that vector. Right? So that's a small tidbit, which is probably not important for this particular talk, but still, it's good to know. Now what you have done is that you have a computer, you have done an evolution on this. Now you want to you want to find out what the answer was, right? For that, there is a mechanism, or there is a formalism to describe experiments which correspond to reading the values, which is known as measurement. So here I'll just do a very high level. There are several formalisms for describing various measurement experiments, but I'll just discuss what suffices for this particular talk, which is basically, if you say that I'm going to perform a measurement in the computational basis, right? And you have the state which I had just written in the previous slide, a couple of slides ago, right? This was the state vector. Then what it means is that you see, so this is from 0, 1, 2, 3, all the way up to 2 to the power n minus 1 basis vectors are there, right? So it sees a 0 with probability mod alpha 0 squared, 1 with probability mod alpha 1 squared, and this label 2 to the n minus 1 with a probability of mod alpha 2 to the n minus 1 squared. Right? This is a subscript. It doesn't appear like that, but it is a subscript. So this tells you basically, if you have a particular state, so you want to measure, in the sense that you want to read out, you want to figure out what that value. So you want to obtain an outcome of that experiment, it essentially tells you, predicts the probabilities of the outcomes. Will it be 0? If it is 0, it will be 0 with mod alpha 0 squared, and so on and so forth. Okay, and after this, there is another notion of what the state vector is after performing a measurement, etc. We'll not go into that because that's not really pertinent to the direction we are taking today. Well, it is pertinent, but probably anyway, the concern, if you look at the depth to which we will go, it's probably it doesn't matter at all. So, okay, so this is what it was, right? The picture again. If you look at the picture again, so there were these qubits, and there are these qubits, and then there are these unitary transformations that are applied one after the other, and then you can do some measurements here in the middle, or measurements somewhere later on, and so on. This basically, and you can do this. You can repeat this several times. You can do some classical post processing in between, somewhere. All of that, this basically comes under the circuit model of quantum computation. Okay, so any quick question at this point? If there's any quick question, we'll stop for half a minute. Otherwise, we'll do this. We'll basically diverge from the circuit model at this point. Okay, so I suppose there aren't. Are there any questions? Okay. Am I audible?
Yes, sir.
Okay, thanks. Okay, so now what happens? We will go back to this Schrodinger's equation, where I said that this Hamiltonian, this particular matrix, or this particular I'll just call it matrix for the sake of simplicity, because that probably doesn't matter for us again in this talk. We'll call this the Hamiltonian matrix, right? Now let's look at this Hamiltonian matrix a little bit more carefully, right? It's a Hermitian operator in the sense that it's the adjoint of the operator or matrix. Adjoint is basically what is in the adjoint. It's the complex conjugate transpose. You take the matrix, take the conjugate of all of its values, and transpose it. What you get is this H dagger. So Hamiltonian is a Hermitian operator, which means that the adjoint is the same as the operator itself. Okay, and as a consequence of this, it is also normal in the sense that H and H dagger commute. Okay, and another theorem which says that there is a theorem which says that if a matrix is normal, or an operator is normal, then and only then is it diagonalizable. What do you mean by diagonalizable? It means that you can write, there exists some basis in the Hilbert space in which you can write this particular operator as a diagonal matrix. Okay, so so this is basically, therefore it can be expressed in this form, which is, I mean, this is, you can for the moment I just so this is the outer, what is called as the outer product notation, which is used in quantum mechanics a lot, but essentially what it means is that you can actually write this as a diagonal matrix. Okay, where each of these EIs are basically the eigenvalues. Okay, of that operator. So you can, so imagine a diagonal matrix where the eigenvalues of that operator sit on the diagonal, right? Everywhere else it is 0. Okay, so an important property of Hermitian operators is that their eigenvalues are real, right? Now this works nicely because these eigenvalues are actually the eigen energies that the system can have in the stationary state, right? So if you look at so in other words, let me summarize. If you look at the Hamiltonian, which is a Hermitian operator, and therefore it has real eigenvalues, right? So these eigenvalues of that Hermitian operator are the energy values that the system can take. Okay, and these are exactly the energy values that the system can take. Okay, why are we interested in this? So this Hamiltonian is therefore very closely associated with energy, right? So that's one association that let's keep in mind. Okay, and now with this we can also talk of Hamiltonians that are acting on qubits. I have a small picture in the next slide, which will hopefully make things a little bit more clearer. But the point I'm trying to make here is that you can define and you can of course construct Hamiltonians which act on a bunch of qubits, right? Each Hamiltonian acts on a constant number of them, independent of the input size. Okay. Overall, if the number of qubits is n, you don't want to have Hamiltonians that work on n, where n can be arbitrarily large and so on, right? So you want each of these Hamiltonian to work only on a constant number of qubits, and then you put together a larger Hamiltonian, right? That's how it is, right? So even in circuits, classical circuits also, you have these gates which operate on only a constant AND gate, NOT gate, NAND gate. There are gates which operate on a constant number of inputs, and then you put together those inputs, those gates, to realize any arbitrarily combinational circuit that you want, right? That's how it works, right? So similarly here also, you want these Hamiltonians to act only on a constant number of qubits. Because we need a reasonable model of computing. We don't want to say that I can in one shot I can give you a Hamiltonian which acts on an unbounded number of qubits and so on. So the important thing is that other than those constant number of qubits, those constant qubits, it acts trivially on the others. It doesn't touch other qubits, right? So basically, what you want to say is that you want to basically influence the energy profile of a small number of qubits using this Hamiltonian. That's what you are essentially trying to do. So this is an example, a rough example. Suppose these red dots here are all qubits. This is one arrangement of the qubits. It is not necessarily this only. It's a square grid arrangement of qubits I have made. So what I'm saying is that all these are red dots are qubits, and the blue dots are, think of them as a Hamiltonian acting on those blue lines on the Hamiltonian acting on these two qubits. So if you look at this blue line, and I have annotated it as H1, it means that you have a Hamiltonian that acts on these two qubits basically. Similarly, H2 acts on these two qubits. H3 acts on so 1, 2, 3, 4 qubits and so on. So 4 is the maximum number of qubits on which you have you look at any Hamiltonian here, think of either this Hamiltonian or this Hamiltonian or this Hamiltonian or even this Hamiltonian. 4 is the maximum number of qubits on which any of these Hamiltonians are acting. Okay. Now what we can do is something interesting, right? So we first of all some notational stuff. If I say H1 of ij, so for example H1, you think of this as H1 of ij. So this is I, this is j. What is happening is it's actually a two to the n dimensional Hamiltonian. It's a huge Hamiltonian that acts non-trivially on only two qubits, I and j, right? Right. So think of it as a very large matrix, right? It's not a small dimensional matrix, but it's a large dimensional matrix. But it has this property that it acts non-trivially only on qubits I and j. Okay. Suppose we have m such Hamiltonians, right? Instead of one here, we have m such Hamiltonians. Here we have one m, right? 1, 2, 3, 4. So there are these blobs that I have made. These are these Hamiltonians, right? So suppose we have m such Hamiltonians, and then you consider some of these Hamiltonians H1, H2, H3, H and up to Hm, right? Notice that recall that each of them act non-trivially only on two or a constant number of qubits, let's say 2 or 3 or whatever, at most 2, at most 3, at most 4 or whatever. But they are basically a 2 to the n dimensional matrices. Okay. Now, finding the ground state of this Hamiltonian could be in general very difficult. Why? Because it's actually a 2 to the n dimensional Hilbert space. What is the ground state, by the way? Ground state is the eigenstate or eigenvector corresponding to the lowest eigenvalue. right? I'm sorry I didn't define this. Ground state, as the name indicates, you look at the eigenvalue spectrum of the Hamiltonian. Okay, look at the lowest eigenvalue, right? The eigenstate or a combination of the eigenstates or eigenvectors, linear combination of eigenvectors that defines that corresponds to this lowest eigenvalue is what is as we are calling it as the ground state. Okay, so the nomenclature also makes sense because we are talking about eigenvalues of the Hamiltonians being the energies, right? So you want, when you say ground state, what you're saying is the lowest energy eigenvalue, and the eigenstates or eigenvectors corresponding to that. Okay, is this clear? Is this definition clear? We are kind of done with the definitions in some sense now. And why are we interested in this? We'll see in a minute. Why are we interested in finding the ground state of this Hamiltonian? We'll see in a minute. Okay, so we take a digression here on 3-SAT. Okay, this I'm sure everybody would be familiar with. Well, anyway, I'll do this again in the interest of completeness. So you have a Boolean formula on n variables, right? And n variables where z1, z2, z3 up to zn are Boolean variables, and it is given in the form of this particular c1, c2, c and up to cm, where each of them is called as a clause, right? Clause, and that each of these is of the form of this. So this is what is called as a conjunctive normal form. Each of these clauses is a disjunction, and it's a conjunction of several such clauses, right? So you look at these disjunctions. It is called 3-SAT because you don't have any clause which has more than 3 such entries, right? So you take any of these Boolean variables, put them here either in its original form or its negation, right? And you have several such clauses, m such clauses, and the question that you want to ask is the Boolean form, is this formula satisfiable? Better still, the question is, if it is satisfiable, first of all, you tell me whether it is satisfiable in the sense that does there exist an assignment of 0, 1 to these Boolean variables such that assignment to the Boolean variables z1 through zn such that this particular formula is satisfied. Okay, that's the question that we want to ask. Is that clear?
Yes, sir.
Yeah, great. So now what we do is, no, this is where we do something. This is where we do something interesting. You consider this energy function, right? This is an energy. Think of this just as a function which acts on the literals. These are also called Boolean variables or literal. Let's just call them Boolean variables, which acts on these Boolean variables in this clause. Right? ZIC is the first Boolean variable which is present in the clause C. Okay, ZJC is the second Boolean variable that occurs in clause C, and ZKC is the third Boolean variable that occurs in clause C. Okay, this function assigns this to this a value of 1 if it violates clause C. In other words, it doesn't satisfy clause C. So, for example, if I say Z1 is equal to 0, Z1 is equal to 1, Z2 is equal to 0, and Z5 is equal to 0, then what would happen is that it would not satisfy this particular clause. Okay, such an assignment is basically given by this function. It is given a value of 1 and it's 0 otherwise. So what is this what is happening? Let's see what's happening here. And this is basically defined for every clause. This function is defined for every clause. So let's see what is happening. If a clause is violated, this particular function, if a clause is violated by a certain assignment, this particular function basically gives it a penalty of 1. If the assignment of the values that are involved, of course, that are involved in this particular clause, others anyway doesn't matter. If the assignment satisfies this particular clause C, then we don't penalize it. Okay, so basically what we are trying to do is give an energy penalty, and this is where the tie-up happens with the Hamiltonian. Eventually we'll see that this is where the tie-up happens. If there is a violation, if the assignment violates a particular clause, it gives you an energy penalty is given, and so and so on. How if it's not given, the penalty is not given. So therefore, if summation of all these functions is 0, right? If and only if all the clauses are satisfied by the assignment, some assignment, right? If all the clauses are satisfied by a certain assignment, what is going to happen is this energy penalty function is going to give 0 to everybody, and therefore this particular assignment satisfies the entire formula, right? It satisfies C1, also C2, also C3, also Cm. It's a conjunction, right? So it satisfies all of this. Okay. Is that clear? So yeah, so with this, what we can do is we can basically associate with the clause C what is called as the local Hamiltonian. This is nothing. So you recall that we had been talking about Hamiltonians and then their eigenvalues which correspond to their energies, and then the corresponding eigenstates and so on. So what we are saying is we construct we first associate with a particular clause the local Hamiltonian like this, right? So this is the local Hamiltonian, right? We'll see why we are calling it the local Hamiltonian. Eventually we'll have a global full-fledged Hamiltonian, but for the moment we're just calling it the local Hamiltonian. What it does is, and this local Hamiltonian is local to this particular clause C. Okay, so this is the consider this to be an eigen vector, and this is the so if you remember, right, if you recall the math definition of eigenvalue, you have AV is equal to lambda V kind of thing, right? So where A is the matrix, V is the vector, lambda is the eigenvalue, and V is the, of course, eigenvector, and so on. Similar, you can see the similar structure here. So you have this matrix, which is basically the Hamiltonian, local Hamiltonian, and you have these eigenvalues and eigenvectors out here. This eigenvalue, remember that we are associating eigenvalues with the energies, right? Hamiltonian's energies and eigenvalues are essentially interrelated, right? So therefore, when we proceed this, for every clause you define such a local Hamiltonian, which basically gives you all these penalties, right? This gives you the penalties, right? So suppose the clause is Z1. This is an example. Suppose this clause is a particular clause is Z1 or Z2 or Z3. Then HC, the function, the penalty function, takes for 0, 0, 0, where Z1 is equal to 0, Z2 is equal to 0, Z3 is equal to 0, it gives a penalty of 1, right? But on the other hand, if Z3 is for an assignment, global assignment where Z3 is equal to 1, it gives you a penalty of 0, right? HC of 0, 0, 1, because then this is going to be 1, and therefore this particular clause is going to be satisfied, so that there is no penalty associated with 0, 0, 1. Similarly, all the way up to only this guy is given a penalty, right? Everybody else is not given a penalty. So HC of 1, 1, 1 is also therefore 0, right? And this is basically, this is till now I've been talking with various notations. This is the first time you see a matrix definition of this thing, right? So this is therefore, so this is, since this is a three-dimensional, isn't it? So 2 to the power 3 is 8. So you get this kind of a thing. So notice that this is the this. So let's look at a couple of things. Notice a couple of things here. So this eigenvalue corresponds to 0, 0, 0, and this is the penalty that is given. All the rest of the eigenvalues, right? This is already in the diagonal form. Therefore, all the eigenvalues, all the elements on the diagonal are the eigenvalues, right? And this is 0, this is 0, this is 0, this is, all of these are zeros, which correspond to various assignments: 0, 0, 1, 0, 0, 1, 0, 0, 1, 1, 1, and so on, all the way up to 1, 1, 1. So only this guy here is penalized, Okay, and in this fashion you get what is called as the local Hamiltonian. Okay, now if you have instead of course you have not just 3, you have n of them. What happens is that you do what is called as tensoring with with identity on the rest of the Hilbert space. So you can actually transform, you can not transform, you can write it as a Hilbert, as a an operator or a matrix that operates on a 2 to the n dimensional Hilbert space. Now, so this is what it is. So consider the Hamiltonian, which is a summation over all clauses. So this is for one clause, this particular Z1, Z2, Z3, this kind of a clause. Similarly, there are m such clauses. So what you do is you sum over all m clauses, what the local Hamiltonians, right? Or local Hamiltonians appropriately scaled up so that it operates non-trivially only on these 8 dimensions, but trivially on all the rest of the 2 to the n minus 8 dimensions. So you get a massive matrix out here, right? Which is of dimension 2 to the n cross 2 to the n. The important thing is its ground state encodes the satisfying assignment or assignments if there are more than one. Right? We'll see. What do you mean by that? This particular Hamiltonian is constructed in such a way that if your assignment satisfies the particular formula, then it skips through all penalties. It slips through all penalties. It's not penalized anywhere, right? So therefore, its lowest energy value remains 0, and the 0 penalty lowest eigenvalue assignment is the assignment that satisfied all the clauses. Okay, that's the basic philosophy idea behind it. So its ground state encodes the satisfying assignment. Okay. All right. So then, but then the problem is, how do you find it? If you have 2 to the n dimensional vector, right? It's already, and you want to find an algorithm. Sorry, you want to find the ground state, or lowest eigenvalue state in some polynomial time in n, not 2 to the n, right? That's we'll consider n to be the input size. I didn't explicitly mention it, so we don't know and the other thing is, first of all, I have the Hamiltonian, which basically describes the energy of that system. How do you even get to that Hamiltonian? How do I evaluate? How do I start? Where do I start my system and say that my energy profile will finally be the as it is described by this particular Hamiltonian output? How do you? So that's the other thing. So we have to evolve the system to this particular Hamiltonian or energy profile first, and then you have to ensure that it is indeed it's in its ground state. You have to cool it down to, so I mean, well, you have to basically ensure that it is in the ground state. Yeah. So now here is the adiabatic quantum computing paradigm. Okay, this is how we'll do it. We'll come back to the SAT example in a moment. Choose an easy to construct initial Hamiltonian whose ground state is also easy to construct. Right? And there are a couple of technicalities. We'll look at that also later, but it doesn't matter at the moment. So what the idea is that you construct an initial Hamiltonian, okay, whose ground state is also easy to prepare, and choose a final Hamiltonian whose ground state encodes the solution to your optimization problem, just like we did here. Right? This final Hamiltonian is something we evolved here, right? Right, and whose ground state encodes the solution to your optimization problem, and then what you construct what is called as a time dependent interpolating Hamiltonian. It's a Hamiltonian. You apply a Hamiltonian in such a way that it changes with time, of course, right? As time progresses, it changes with time, and the physics, the quantum mechanics requires you that the system evolves slowly as per this particular interpolating Hamiltonian. What is slowly, we'll see again in a couple of slides later. So you make it evolve slowly, and you're done. You have the solution, the grounds. So the system, you started with a ground state, initial ground state, and if you evolve slowly, you will initial ground state of an initial Hamiltonian. If you evolve slowly, you will end up in the ground state of the final Hamiltonian, which is exactly the solution to the optimization problem or the SAT problem that we saw. Okay, so with high probability, okay, the conditions apply. That also we'll see in a minute. So let's do more. Let's understand what is more, right? So this is an example. So you recall this again, this Hamiltonian, the Schrodinger's equation. Right now, your h of t is actually dependent on time itself, right? So now, what is called as we'll call it as a interpolating Hamiltonian, right? I mentioned it as an interpolating Hamiltonian, right? It's a ht of capital T. This is one way of doing it, and we for some of the most of the applications that we'll see now today, it will follow this particular format. So and that's why I'm sticking to this. So it's so this Hamiltonian, which is a function of time, with this major total time evolution time, which will associate with the actual computation time. So h of t by capital T is 1 minus t h of 0 plus t by t h of 1, which is the final problem Hamiltonian, right? So eventually it is you are in the initial Hamiltonian when t is equal to 0, and t is equal to 0 means you don't have any component of the final problem Hamiltonian. And as time evolves, this component comes to 0, and this goes to capital T, where t becomes capital T, which means it is h of 1. Right, so it's a linear interpolation between the two this thing. Yeah. So in general, you just say that this is a single parameter family of Hamiltonians, where you say t capital, you denote s by s, this fraction t by t, and this becomes a single so it's a single parameter family because there's only one parameter, which is basically changing this nature of this Hamiltonian over the entire evolution. So that's why it's called as a single parameter family of Hamiltonians. When you do this, right, you get this kind of. This is an example one, by the way. This has nothing to do with any. I mean, this has some. This correspond to some problem, I think, combinatorial optimization problem. But so the point I'm trying to make here is that you get a spectrum like this. So you initially your t is equal to 0. And this here t is equal to capital T. Time becomes capital T. So if you start here, which is the lowest eigenvalue, the state corresponding to the lowest eigenvalue, evolves slowly. What I called slowly, we'll see what slowly means. Evolve slowly. If you evolve slowly, the physics tells you that you will not jump to the next state. Right? If you don't jump to the next state, what happens is you continue to be here, all the way up to this point. You are in this ground state only. But the interesting thing is, or useful thing is, that the ground state of this particular Hamiltonian encodes the solution to your combinatorial optimization problem. So therefore, somehow, if you can avoid jumping to the next eigenvalue, or next energy level, you are basically in a good shape. Okay. Now, therefore, so what do we need to do in order to ensure all of this happens?
MVP?
Yes.
Yeah, so another 5 minutes, can you?
Okay. Sure. I'll take another 5 minutes. Okay, sure.
Okay, fine. Okay. Thank you.
I'll probably have to cut short a little bit, but that's fine. I'll be done with the major idea part. Okay, great. Thank you. Thanks for the reminder. Okay, so then the initial Hamiltonian must not be diagonal in the same basis as the final Hamiltonian. That's a very it's an important criterion, because otherwise what happens is that there is what is called as a level crossing, which means that there is a level crossing out here, which is something we don't want, because then the energy, then you can actually end up in a state here, right? If there's a level crossing and so on. So if it's diagonal in the same basis, then this happens. So that's right. That's something that we should be careful we don't do that. How slow is slow enough? In quantum mechanics, there is this thing called Adiabatic Gap Theorem, which tells you that if the time, that capital T that we have been speaking of, is much higher than, in fact, it should tend to infinity ideally. If that is the case, then we will not have. You will not have. You'll with high probability you'll be in the ground state. So T is should be much greater than this particular quantity, where this is this will remain to be small in most cases. We don't worry about the numerator. This denominator is the crucial thing. Okay? If this gap is exponentially small, right? This gap is exponentially small, then this time has to be exponentially high in order to make sure. On the other hand, if the gap is polynomially small, right, which means that it's not a, it's exponentially small is very, they come very close to each other. Polynomially means they don't, as for computer scientists you'll understand that it comes naturally. If it's polynomially away, then you are in good shape. Your time, you don't need too much time, right? This kind of tells you what time complexities you are looking at. Okay, so then coming back to the, I'll probably quickly breeze through this. Coming back to the three sat, right? The probable Hamiltonian anyway we have seen already. This is a summation of all the local Hamiltonians, and then a good choice for the ground state of the initial Hamiltonian is this uniform superposition of all possible assignments, right? Which basically any assignment is equally likely, in uniform superposition is a feature of quantum parallelism, or it's kind of famous by the name of quantum parallelism and so on. So initially everybody is equally likely, and then you come up with a good choice for the initial Hamiltonian for this, which I'll probably skip this in the interest of time. And then you get a, this is for 1 qubit. So very by this particular paradigm itself was proposed by Fari et al. In about 2 decades back. And for a single qubit thing, this is one spectrum that I'm just example just for showing that this is a sufficiently large gap. It's a toy example, of course, but this is what you want to do. So the gap should be low, basically, right? And then there is this unordered search for Grover search, which I'll skip this. Those who know about Grover search, it's a very classic example of quantum. It's a classic algorithm, well-known algorithm in quantum computing. So here, this is an example of where the gap really comes down drastically. Right, so and therefore you just get what is, so you get a quadratic speed up over classical algorithms for unordered search. Only so it's only just merely a quadratic speed up, and that's what you observe here also. Okay, so there are other ways of doing it. So how do you, every time when a combinatorial optimization problem comes up, is there a better way? I mean, is there a kind of a slightly generic way of figuring out these problem Hamiltonians? The spin glass icing model, which is again probably will be well known and identifiable to physicists. Right? This gives you a very nice framework for posing combinatorial optimization problem. I think in the interest of time, I'll skip this also. But what is to be noted is that many hard problems, NP hard problems, can be stated on the icing model, and therefore you can basically just directly use it for quantum adiabatic quantum algorithms. So it has advantages. Natural to pose combinatorial optimization problems in this paradigm. It has been shown to be equivalent in power to the quantum circuit model. Right, that's a very important result. Right, and it was expected that it will be robust to decoherence, and which is a problem in quantum computing, and errors in implementation and so on. But then there are issues. Success is guaranteed. If you really want to guarantee it works only at t as t tends to infinity, otherwise not. And success probability is generally not monotonically increasing with t. Then we I'll stop in just another minute. And also, what if we are only happy with just an approximate solution to the optimization problem? I don't really want to find exactly optimization, most optimal solution. I'm okay with an approximation. Then what do you do? Is there some way of doing it? This is where I think the same team, Fari, Goldstone, and Gutman in 2014 came up with what is called as quantum adiabatic approximation algorithms. Sorry, so these algorithms, approximation algorithms, QAOA. And which basically again, it's basically think of the adiabatic evolution of the Hamiltonian evolution, take that and think of it as some kind of a piecewise linear interpolation kind of a thing, and what you do is you basically get a sequence of unitary transformations instead. Okay, and then you get this thing. Okay, so that's it. I thought I'll go into details of this, but I think I'll skip here. Yeah, thanks. Any questions? Probably I will take some time for questions.
Thank you so much, sir, for your time.
Yeah, no, my pleasure. I wish I was there.
Yes, thank you, MVP. Thank you so much.
Thank you. Thank you.
Thank you, thank you, thank you. Bye.
Yeah, bye.
Here or there? Not this one. No, it's here on this one. Okay then.